So when we compared these Venturi meters, the advantage of these, first of all, it doesn't have differences compared to the weir, the potential energy differences compared to the weir. It enables to have a measurement in low pressure drops as well. It's suitable for unclean water if you have a high water cut. So it's suitable for unclean water as well. It can measure without having any problem. It's very good. It shows a very good performance in especially in wet gas measurements. We described these wet gas, dry gas, retrograde, volatile last week, right? These types. So it's good at wet gas measurements. Okay. But it has some challenges and points that device can have some problems. It does not applicable with the non-linear flow characteristics. Just has to be a linear flow to get a good results. Channel constriction resulting in damming of the heat water and risks of the deposit build up in the event of velocity decrease. Sudden velocity decreases can give some problems in this. Gives the loss of fluctuations. Actually, these fluctuations will be harmful for your data. So it has risks of plugging through larger floating items. Backflow is one of the biggest problem in here. If you have a backflow, then it makes your measurement impossible. You cannot expect any correct results with this one. Backflow is one of the main problems. These we were facing when I was in Basra. We were facing with this one. What happens when the tanks, stock tanks, are full? Okay, but you want to continue to your flow without knowing it. It's operational issue, of course. Without knowing it, you want to continue to your flow, but your tanks are full, so it's making a backflow. So because of that, directly you are seeing very big fluctuations in your data. So gives very high error percentage at that time. You cannot get any production results. Okay. So it's one of the main issues of this Venturi meter. And quality and reliability of the measurement, depending on the connected sensor, is another issue. The connected sensors, the quality of connected sensors is one of the main issues as well. If you have a bad quality one, so you can your error percentage increase. Some companies, some mid-range of companies are using, for example, the Venturi section in different company, and they are putting their own sensors, pressure sensors, so it creates another problem as well. These tools have installation costs. It's costly, like Coriolis meter. Initial costs are high actually. So this can be given to Venturi meters. Another one is the positive displacement meters. Okay. Positive displacement meters can be in different types, like different shapes as well, like overgear piston, rotary, rotating disc, etc. So this can give the conformity of using the correct shape according to your design. Okay, design of your production line. Another thing is excellent in dealing with the steady flow rate in a pipeline that has a diameter of 10 inches or less. Above 10 inches, it creates problem, increase the uncertainty on your data. But below 10 inches, you can give, if you have a steady flow, you can get good results. Applicable in low flow rates with high accuracy. So especially we were using this one for low flow rates. With low flow rates, your accuracy will be higher compared with the higher ones. Okay. So positive displacement, one of the negative effects on the measurements. Positive displacement flow meters doesn't have required industrial approvals for application in the field. It doesn't have too much applications currently worldwide, so it needs to be approved in the field side. It definitely needs to be approved in the field side, and the standardized also. And this is needed as well. But in the future, it will be one of the good selected preferred meters, of course. So vortex meters. Actually, these vortex meters, a vortex flow meter measures flows of liquids, gases, and steam by sending the frequency at which vortices are alternatively shed from the bluff body. Okay. The frequency at which the vortices are alternately shed is directly proportional to the flow velocity. Flow measurement performed based on the vortex principle in here. Inside each vortex flow, a meter of the bluff body is located in the middle of the pipe. Okay, so this body is a kind of obstruction that disturbs the flow, and the vortices are present either the side of the bluff body and are carried away by the flowing fluid. The zones of high or low pressure appear downstream and thus create a phenomenon that's known as the Karman vortex street. So it's much more detailed technical part of this. This Karman vortex street, it used this one to have the measurement. Okay. These vortex meters are extremely versatile, can measure the liquid, gas, and steam. It gives relatively high accuracy compared with the others. Okay, it doesn't have moving parts, so it's simple design it has. This is a very good advantage. Also, multivariable meters provide mass flow measurement. The tools have API standards developed for the use of custody transfer. This is an important one because if when you use these standards, you guarantee that you will not have decrease the risk of having any problem on your device. Okay, so this is a good one. The problems, the negative things about these meters, it can cause some pressure drop due to the presence of bluff body. Okay, there can be some sudden pressure drops. So these affect the results of rates. And of course, still, it's the custody transfer is limited. Okay, it has a standard for this, but it is limited. But in close future, this will be more widely to transfer as well in terms of transferring and in terms of usage. Okay. The Orifice meters, these instruments are one of the well-known ones, actually. One of the well-known ones, and it's cheap ones because being cheap, the companies, especially mid-range of companies, are preferring this too much. So this is an instrument. That records the flow rate of gas, especially. We are using this for gas measurements through a pipeline. The flow rate is calculated from the pressure differential created by the fluid passing through an orifice of a particular size, of course, and other parameters such as static pressure, temperature, density of the fluid, and of course the size of the pipe. Okay. So the advantages of this, the orifice is small place and easy to install and remove. It offers a very little pressure drop, from which 60 to 65% is recovered. Okay, this is a good advantage. Because when it requires large pressure drops, your fluid cannot assess this one, your wellbore fluid, so you cannot have a good measurement in this case. The orifice meter can be easily maintained. This is a good one. Wide range of flows it can measure as well, but mainly are using it for. They have a simple construction, easily fitted between the flanges. Very simple design, so it's very easy to make the construction of that. and fit the instrument in between the flanges, as can be seen in the picture. Okay, here in, for example, these are the flanges. Okay, these are the flanges, and you can put your orifice plate directly to here. And how it works, it's according to the difference of the volume that the flow is going through. It calculates by using the data in your orifice plate. Okay. Of course, they are the most suitable for most gases and liquids. I said they are very cheap compared with the others, and the price doesn't increase dramatically with size. According to the size, doesn't change when compared with others. For example, Coriolis meter size, the price changed with the size a lot. Okay. So, what are the challenges and problems we are dealing with for orifice meters? It requires a homogeneous fluid. It's one of the issues. So, because of that, we are using it for gas. Because when you go to, for example, when you are measuring the retrograde fluid or volatile fluid, whatever, so your error percentage increases directly. So, requires single phase liquid. It requires the flow of axial velocity vectors, some more technical. It causes a pressure drop in the liquid. Of course, there must be a pressure drop. You are trying to satisfy that pressure drop because the design shows it as well. Okay. The accuracy is affected by the density, pressure, and viscosity of the fluid. Of course, like the others as well. This is surely. The range of measurement of viscosity limits of fluids. Viscosity can be a problem as well in here. For heavy oils, your error percentage will be increased as well. Okay. It requires straight conduits to ensure accuracy is maintained. Okay. The pipe must be totally special for the measurement of the flow of liquids. It has low range capacity. These can be given as the challenge of these orifice meters. So I tried to explain the single phase meters to you. Okay. So let's go through to separation based techniques. Okay. What are the separation based techniques? Sorry. First of all, the rate measurement accuracy and the resolution is quite important in well test analysis. For example, reservoir engineers often complain about the lack of reliable rates and rate inaccuracies as well, because how accurate you get your results of rates, you can use it. You will use it in the interpretation of your downhole. For example, especially in cleanup period, it's with the conventional techniques, it's impossible to get the cleanup period rates. Okay, this is crucial, earliest time rates, and they are very crucial to describe the parameters of your reservoir, your permeability, skin effect, your porosity, and the behavior of your reservoir in your well test analysis. So it's very crucial to gather the rate results correctly. Okay. So secondly, the separation is one of the simplest way to measure the flow rates of each phases separately. It also brings some sort of problems which can make things difficult. Okay. It simplifies the problem of determining the velocities as fractions. However, the quality of separation becomes critical and one of the most important factors which affects the error percentage and uncertainty on your measurements. Okay. So additionally, there is a need to use some indirect inputs. For example, rotation speed for the vortex meters, for example, rotation speed, pressure differential, as I mentioned. So these requires extra calculations, and these calculations gives you the results that you are getting is the result of these calculations because quantitative measurements. Okay, so in spite of the direct measurements, you are making the measurements with as a result of calculations. Okay, measurement plus calculations, so increasing the error percentage. Okay. So these extra calculations make the work more human dependent. Thus, the operator reliability and intention becomes crucial in separator-based techniques, separation-based techniques. Okay. So herein we can see the diagram, classical diagram. Your reservoir pressure and temperature, your well bore, you are reaching to your wellhead, your wellhead pressure and temperature, and you are passing through to your line. You are in your line conditions. Mostly we are putting, but if a company want to use multi-phase flow meters, your multi-phase flow meters will be mostly in this part. Okay. Of course, some other versions that you can use only in single phase. I am not accounting these ones for multi-phase flow metering I am talking about. For multi-phase flow metering, your device has to be put in here in line conditions. It's very important. It will not be separate from the line. It has to be in your a part of your line. This is one of the crucial points. And then we continue to our way. We come to our separator. Your separator pressure and temperature you separated your liquid, gas, oil, water, and gas, of course. So you have, you calculate your certain rates of each phase in here when it goes out from your separator, and then you put it to your stock tank. Your oil comes to your stock tank, gas goes according to the situation. It can go to flare, it can store in somewhere. But for your oil, it is taken to your stock tank to wait to become that oil. Actually, after a while, it becomes that oil. Some part of the gas which included inside the oil as a solution has gone out as well, as I mentioned in the second week. And what happens? Your that oil, your stock tank oil, becomes available after 12 hours at least. Okay, and you separate your gas, another part of your gas in here too. So of course, all these steps will have different phase diagrams. Okay, you have different phase diagrams. Let's pass to this phase diagrams. For example, in your reservoir, you will see a phase diagram like this. What type of phase diagram is this? When we compared it to last week, I can say it's volatile, nearly volatile, but it can pass to retrograde as well. Okay, according to the shape, I can say that it's on the way of passing to retrograde, but on the volatile part, right? So in your reservoir, it comes through to your wellhead, your wellhead conditions change, and your phase diagram also change. Okay, it comes to your line conditions in your multiphase, your phase diagram will change again. In separator also will change, or also separation will occur. Your after separation, your gas phase diagram will be like this, because according almost dry gas you have, right? Almost you have dry gas. So in your oil also, the shape of your phase diagram will change as well. So when it comes to your stock tank, of course, your phase diagram of oil will be more white. It will be widely shaped, it will show. And gas will show nearly close to a line. It will show something. The balloon, we say, balloon shape will be close to a line. Okay, so we have to assume when we are making our calculations, all of these, according to the situation where we are measuring, okay? So fluid phase diagrams along the production, for example. As I mentioned, the big phase diagram shows actually the fluid characteristics in your wellbore, right? So this is your initial reservoir condition. Your bubble point pressure is here, your critical point here. Reservoir fluid phase envelope described in here. So what's going on when it comes to separator? So separator oil envelope will be like this, and gas envelope will be like this. Okay. Because why? Because the composition of your fluids changed. Composition changed. Because of the composition changed, your light components will be separated from the heavy components. Heavy components will form a diagram like this, and the light components will build the diagram like this. Okay, so according to your composition, your phase diagram changed directly. So when we compared according to this main phase envelope, which includes the composition in your reservoir, in your valve also, same composition nearly. So according to this phase envelope, we have to describe some certain points. What are these? Initial reservoir condition. Okay, first of all, your initial reservoir condition, we call it PI and TI, right? So your bubble point here, your multiphase flow meter conditions. I gave the example here. Your multiphase flow meter conditions, your separator conditions, and your stock tank conditions. Okay, we have to describe these 5 points by measurements, of course, by measurements. So the CGR, condensate gas ratio, and GOR, gas oil ratio, the ratio of these two also need to be described. This is the function of the separation process actually. The test should emulate that independently of metering conditions. So when you describe this ratio, it can give you the idea how much your composition changed. Okay. So for example, in here your phase envelope is available. For example, 3000 psi, 190 degree Fahrenheit. Your condensate gas ratio measured as 64.6. It changed to 83 when it comes to 2000 psi with 160 Fahrenheit. And 1000 with 100 degree Fahrenheit, your condensate gas ratio comes to 97.7. Okay, so it directly changed. So each point is crucial to make your measurements. Okay, your measurements in your separator, in your stock tank, multiphase flow meter, as well as your wellhead. So in the surface part, it's crucial to describe each parameters of these, and you have to make your rate, pressure, temperature measurements, each steps, each parts and tools. Okay. Yes, here in condensate gas ratio is changing by time according to your place. According to your place, sorry, not time. According to the place, that's your fluid flowing. Okay. So the separator performance. Okay, let's talk a little bit about the separator performance. For example, in a very well designed and applied separator test, let's assume that we have everything is on the way. Very efficient test we had done, very well designed and applied the separator test very efficiently. Even in these conditions, the separator can show you plus minus 0.1 accuracy. Okay, but in these measurements, you have to ensure that each device is within its operating range. Each device is properly calibrated on time. All inputs are accurate, and you are interested in race at metering conditions. Okay, so I am assuming that everything is on the way. All devices and sub tools are working on the way. Okay, working correctly. But this is theoretically, of course. In the practical applications, this could not be satisfied. Okay, could not be satisfied. It's very hard to satisfy it. I did not see any case like this. So the separator uncertainties are essentially unknown and very dependent to its measuring conditions. Okay. So it's important to note that typical accuracy when we compare to all cases, of course, more and less, but the typical accuracy range is between 5% to 10%, we can say. It's far, far away from plus minus 0.1% accuracy. Okay. So in many cases, you need to have more accurate measurement results. And multiphase flow metering satisfying this one in most of the game and satisfies this one. Okay. So at this point, we said multiphase flow meters involves to the game. So let's see the market and what type of devices we have as multiphase flow meter using in the oil and gas industry. So these are the main multiphase flow meters available in the market currently. Of course, some new technology development versions of these available, but mainly these tools are dominantly used in the market. It's Halliburton tool. Expro and Roxar has multiphase flow meter. Schlumberger phase tester and phase watcher. Weatherford Red Eye it has. Roxar has Vector. Medenk, Solartron, and Hymo also has multiphase flow meters in the industry. In the future, when you see these names, so you have to be familiar with this one. That's why I'm giving this slide to you. Here, in what we can say in terms of the performance and effectivity, also there are some case studies available in the literature which compares some devices. As I know, one of them from Oman, and compared these devices. And the Schlumberger device, the phase tester and phase watcher, has far away in terms of the performance and the rate results. The validation tests has been performed. It is far away. It shows a good accuracy and better performance compared with the others. So in some part of my presentation, I will go through how it used and its working methodology, calculation overview. I will try to give these ones as well. Okay, so these multiphase flow metering, when we separated the phases as exploration, development, and production. For the exploration phase, three main multiphase flow meters are separated from the others. Okay, these are, as I mentioned, Schlumberger phase tester and its mobile multiphase flow meter as well. Halliburton device and Roxar also shows better performance in terms of exploration. Why we are saying in the exploration? Because in the exploration phase, you just finished. You have limited wells in your field, right? You have limited wells, 1, 2, 3 wells, whatever. So you are in exploration phase. You don't have any idea regarding the reservoir flow, your zones, the productivity of your zones. You are not sure about that. So your ranges are not known well. Okay. Because of that, devices has to be, as the accuracy of the measurement devices are very crucial in this point, right? So according to the case studies and literature reviews, these three devices shows a better accuracy compared with others in exploration phases. So when it comes to the development and production phases, of course, you have more idea regarding your reservoir. You know what type of fluid you are producing, what are your productivity index, okay, what type of recovery you have from your reservoir, right? So because of that, you have more idea regarding on the characteristics of your field. So at this case, you can use, of course, Schlumberger device, Halliburton, Expro, Weatherford as well, Hymo and Medenk are useful when you are making in the future, if you face with this type of issues, when you are making your decisions. First of all, you have to describe which part of the which phase I am in my field. You have to describe this one, and then according to that, you have to select your tools. Okay. So another thing is when you pass to production part, what happens? You can of course use your mobile multiphase flow meters, but also there are some permanent multiphase flow meters as well. So what's happening? These are Schlumberger device is of course one of them, the phase watcher. Vector, Hymo, and Solartron has another permanent devices. Okay. So these are used in the field directly without taking it out. Okay, it becomes a part of your well, your field, your line, and stays in there. Okay, these companies also, as far as I know, they are also giving the training to the crew as well. The training to the crew. Some of them maybe maintenance I don't know, but giving the training to the crew to use the device correctly and making the maintenances. For example, for Schlumberger, as far as I know, they are coming in every 6 months. The Schlumberger crew making the to make the maintenance and to ensure that everything is on the well. On everything is going well actually. So these 4 devices can be used as permanent multiphase flow meters as well. Okay. So okay, we mentioned the single phase meters, so we gave the types of them. Now I would like to give the types of flow of multiphase flow meters as well. Okay, so these are Venturi meters, cross correlation meters, single energy gamma measurement, the meters that make single energy gamma measurement, I will mention in details, electromagnetic measurement devices, microwave devices, ultrasonic devices, and the latest technology, the dual energy gamma devices, which compared more accurate compared with the others. Okay. So let's start with the Venturi for multiphase metering. So these Venturi devices actually can make a robust mass rate measurements with moderate sensitivity to fractions compared with others. Okay, moderate sensitivity we can say. It's quite straightforward measurement given a good density input. So your densities has to be very accurately measured, because density is one of the dominant factors which affects your rate results directly. Okay, so non-intrusive and well accepted. These are the strengths of these devices, we can say. But the weakness, it's designed for a single phase flow. When it passes to two phase, so your errors on your rates are increasing. You are starting to see more fluctuations. Okay, more fluctuations. It affected by discharge at high viscosities. Viscosity is still a problem here as well. Application to multiphase flow strongly dependent on a good slip law flow model. Okay. These are the characteristics of the Venturi device for multiphase metering. So another one is cross correlation. Cross correlation device. One of the examples is MFI cross correlation velocity meter can be seen in here. The strengths can be given as direct measurement of phase velocities, not requiring slip correction. It's a good one, because the device is simple when compared with the others, as you can see from the picture as well. So white velocity turn down it has. And the weaknesses, it assumes that the presence of markers in flow. Okay. It assumes that the flow is a stable flow. Okay, it doesn't have any fluctuations. It assumes this one. So it can be affected by the distribution of components. For example, you had some condensate banking in your wellbore, condensate banking, heavy components parted in your wellbore, and with the wellbore, that heavy components start to move through your multiphase meter. When this meter faces with that components, so directly it fluctuates. It could not separate that. These are a kind of condensate banking. Okay, so it's a bad problem, because it shows the same thing for foams as well. Foaming can be an issue when there is a foam in your wellbore. This also shows some fluctuations and increase error percentage. So single phase gamma, this uses the direct density measurements. It's relatively simple inputs with moderate margin for error. Okay, acceptable. It has a simple measurement independent of flow distribution, and it does not require gamma windows. It does not require gamma windows because it's just using the single energy gamma. I will explain these one, what I mean. it's a little bit, it uses a nuclear source, okay? It uses a nuclear source, and from this nuclear source, the gamma ray photons collide through to your line, okay, through to your line. As I mentioned, it becomes the part of your line, right? Your flow is coming directly, and this gamma ray photons passing in cross section as a line, and what happens? It collides with the molecules of your flow, and according to that, it gives you a result, okay? So, gamma windows is these gamma photons has a window, okay? This gamma photons has a window, and some points which shows some peaks, okay? So this just use one peak. Because of that, it doesn't require the whole gamma window. It just requires one peak. It just uses one peak. So the weaknesses, it only provides density leading and requires additional fraction measurements, typically water. So it's not good for water measurements in here, okay? So this is the earlier versions of the dual energy gamma systems. Because of that, it has these side effects, okay? So it has some sensitivity on composition that's oftenly ignored, okay? The composition changes. It shows some varieties, but oftenly this ignores. This is the, so what happens? It of course it increases your error percentage. Okay. So let's pass to another one, electromagnetic measurements. I will turn back to this single energy gamma when we are doing gamma because the improved version of that. So electromagnetic means this used direct measurement of water, okay, water content. It's robust to hydrocarbon composition as permittivity is quite invariant to non-polar hydrocarbons, okay. This is the good one because, for example, the dual energy gamma, when you have a water, okay, you are producing just water, 90%, 95% water, or you cannot put it to any other parts. For example, you just want to measure your water, you cannot do it because it has been described according to oil, gas, and water. Okay, you have to describe all three. You have to give input to all three. Okay. So this is a strength for electromagnetic measurement. Okay, but the weaknesses, it depends on structure of flow. For example, bubble size, elongation, continuity. These affects the results. It depends on water salinity. Water salinity, when the water salinity increased, or you cannot give water salinity input, okay, or different input you give, your rate results change a lot. So this is another problem. It has iterative solving, not direct physics. So it works, the calculation works with the iterations, okay. The capacitance shortcut in water continuous flow and inductance in oil continuous flow. These are the weaknesses of the tool. So another one is the microwave measurements. I will describe the microwave measurements as well. So in these tools, the transmission measurements can capture resonant frequency and be a good measurement of permittivity. This is a good one. Provides both water fraction and properties. That's good one as well. Measurement resolution currently actually we said low. Okay, measurement resolution low, not now. It's not. Some companies are producing these tools, and they are saying that the accuracy, the resolutions are in these values, but it's a little bit tricky, and it's a little bit tricky, and it gives a kind of problem, of course, to you. Okay, so herein. I will go through to weakness of this. Okay. There is a question, I think, what is permittivity, they said, right? I'm checking from here. Okay. So permittivity, what we can say, permittivity is a constant value that we use it in the calculations, and it says it gives the amount of the dielectric constant. Okay, dielectric constant. So it's a technical value. It's a technical value. So we have to go through the calculations of these microwave measurements, but it is, we can say that it's a kind of constant change from one measurement to another, actually. Okay, according to the characteristics of your fluid, it changes from one measurement to another. Okay, so that's what I can say about the permittivity. Okay, so what we said, it's complex model to invert, simplified through correlations. You are welcome. And the measurement can saturate sensors. Okay, so when we compared all these measurement tools, actually, we see error percentage, which some of them are higher than even separator results. Okay, some of them is lower, of course, some of them is higher compared with separator results, especially if you are using a new technology separator. You can get close results to new versions of the multiphase meters as well. So from this point, I will continue with the one of the latest technology and one of the best methods that applied in the industry. We call it dual energy gamma system. Okay, dual energy gamma system. This dual energy gamma system is collocated fractions measurements. Okay, it's the strengths, we can say, it's collocated fractions measurements. It gives you the measurements of your fractures, first of all. Okay, it unaffected by emulsions or foam. As I mentioned, there was a condensate banking and foam flow. It can fluctuate a lot, right, in the previous devices. So this is unaffected by emulsions and foam. The hardware is simply simple hardware it's using. It's a single physical phenomena for both gas liquid and water liquid ratios. Okay, when you are when you are calculating these, it uses a just single phase, single physical phenomena I will mention. It has certain rates of individual phases in lower error percentage and less inaccuracy compared with the other techniques. Okay, so the weaknesses we can mention here. It uses reference measurements. Okay, the attenuations, the mass attenuations that you get as a result of these reference measurements are crucial. Okay, you have to make correct measurements, and the device is so sensitive to these measurements. Okay, so another thing is sensitive to composition change as well. Sudden composition change, we can say. It affected by high frequency noise. Multi-energy sources create downscatter and measurement challenge. I will mention these as well. When we give the calculations, we will be more clear. So it has limited accuracy on small fractions compared with the other. It has limited accuracy on small fractions compared with the other tools. Okay, I can say compared with the other tools. So I will go through one of the best tools in the market, the VX of Schlumberger. Okay. And the working mechanism of these as a dual energy gamma source. Okay, I will continue with this tool from now on.